I normally don't make a recording unless things get complicated enough for me to keep track of it all. So I've had these insights about magnetic remanence versus permanent magnets. And the only difference between them is that one is treated with heat and the other is not, while both are treated to a magnetic field, namely iron, in a... and the other difference is, since you can use heat, you don't need a toroidal loop to maintain the magnetic loop, the flux loop. All you have to do is apply heat to rearrange the molecules of the future to be made permanent magnet. Now the difference between them, see, the core of a iron transformer is acting as a capacitor, a magnetic capacitor, when it transfers energy from the primary to the secondary. Not unless the core of the transformer is heated sufficiently enough to turn it into a permanent magnet will the influence of the primary induce anything along the lines of true magnetism to the core. Otherwise, it's simply magnetic capacitance. What's going on is that unless we have heat allowing for the reorientation of the molecules of iron inside a blob of iron, without heat, the most we can hope for is to create remanence, which means there's a capacitive charge going across the surface of each iron molecule without reorienting it. Now, if heat is applied, now they're free to move about and reorient themselves and give us a permanent magnet. But without that heat allowing for the gyroscopic, let's say, all directions mobility of each iron molecule, the most that we can hope for is a capacitive charge. That means that a permanent magnet holder experiment or demonstration popularized by Edward Leedskalnin is not magnetism that holds the pieces together. It's capacitance. It's the dielectric force that glues the two surfaces together, even though it's traveling through a magnetic medium to do so, a magnetizable medium to do so. Not through copper, and certainly not through a dielectric. So it's what the electrostatic force, how it influences ferromagnetizable material in a way that induces magnetism, but only as a side effect, because it's ferromagnetizable. Otherwise, it wouldn't induce that, and we wouldn't even notice a whole lot of electrostatic force necessarily having any impact on gluing anything together. But that's what it amounts to. It's like a dual nature. Now, the reason for all of these distinctions is to try to figure out what was meant by William Lyne's quotation of Nikola Tesla: for every 200 pounds of iron added to a special generator, 1 horsepower was increased at the output. What he was doing was, he didn't tell anyone, but he was creating a temporary magnet, a solenoid, inside a special generator. And the iron magnetically coupled to that core of that solenoid, those two horseshoe solenoids, the iron extension was serving as a capacitor. So basically, magnetic remanence is magnetic capacitance, but you can substitute capacitors in its place and still get the same effect, so long as the source is a permanent magnet. In other words, a DC current. So remanence is a DC phenomenon, and yet it's a capacitive phenomenon. It's a DC capacitive phenomenon. And that's the purpose of the iron. 200 pounds of iron is not the 200 pounds, but 200 pounds fashioned with sufficient surface area to create capacitance, and also sufficient looping surface area to create inductance. Two types of consequences of surface area. But that's the significance. So when he told the Germans to install a special generator bolted to the floor of their battery room of their electro U-boats, he was giving them only one way to increase the power of the special generator, by using the shell, the circular hull shape of the electro U-boat, to add capacitance and inductance to the core of the solenoids, the horseshoe solenoids of his special generator. But the other way to do it is to add capacitors. And then you can do away with the massive tonnage of the hull of an electro U-boat vessel and substitute. So this is basically an ideal transformer in which you replace the core of a transformer with permanent magnets. And if you have 4 rod-shaped permanent magnets oriented in pairs that are aligned with each other, but then the opposite pair is an opposite polarity, in other words, on a diagonal. So you make a square arrangement. When you look down the length of your permanent magnet, rod-shaped permanent magnets, opposite corners of the square arrangement are the same polarity. So you'll have 2 north poles on opposite corners and 2 south poles in between on the other 2 opposite corners. And this creates magnetic loops that are going in opposite directions and cross each other at right angles. No, actually, it's the other way around. Oh, so maybe I got it wrong. Let's see. No, they would go parallel to each other, wouldn't they? There'd be 4 of them, actually. Oh, we don't need that many, do we? Let's see. Positive to negative. Oh, I see. So the ones that are going in parallel are going at right angles to each other. The ones that are in opposition are in a parallel arrangement, opposition of polarization. Well, in any case, that was the idea, was to have 4 rods, 2 of them flipped in their polarity of poles. But that's the core of an ideal transformer. But in order to get more power out of it, you either add capacitance, usually in pairs, in series with the let me think. Right, in series, shorting out, basically, the terminals of the transformer. Or you add iron, bolted, coupled, magnetically coupled, to the endpoints of those permanent magnets. That's why he used a horseshoe shape, I guess, because then he could have them meet together and be bolted to the floor. In any case, of the electro U-boat. In any case, an ideal transformer is a transformer that has DC capacitance stored inside of it, and that's a permanent magnet. But you got to have more than one, and I think it's 4, not 2, because you got to have the DC orientation of magnetic looping, because that's what a permanent magnet is. It's a DC magnetic orientation of flow, equivalent to a solenoid, a DC solenoid. It'll form a magnetic loop coming out of the ends of one permanent magnet and entering the ends of the other if they're oppositely oriented, but that only creates one magnetic loop. So now you need another magnetic loop involving 2 more rod-shaped permanent magnets with the poles at the ends of the rods to create a magnetic loop going in the opposite direction, because now when you have this core, you want to subject it to an oscillating magnetic field coming from the primary, going to the secondary, and back again, from the secondary back to the primary. And That means you need the DC orientation in both directions simultaneously, so that whichever direction is being applied by a coil, it'll have one magnetic loop to augment it during each half cycle. It'll always have one loop to augment itself and not entirely fight it. The other one is there fighting it. Of course, the net, if all four permanent rod-shaped magnets in the core of this ideal transformer are equal strengths of magnetic strength, then when the primary, let's say, applies it one half phase of its alternating cycle, it'll be a net gain, because the two rods that are in opposition to each other, each pair of two rods, cancel each other out. So you'll still have the transference of energy from the primary to the secondary, but you'll have an added DC boost. I don't know if that's called a DC bias or not. I don't even understand what a DC bias means. Oh, but that's usually applied to a frequency generator, a voltage source sine wave generator, that's right. So I'll have to look up what a DC bias means, but that only applies to a signal source. This has to do with a primary, let's say, transferring a signal through the core of a transformer, and what impact it'll have depending on what we make the transformer core out of. Now, obviously, a permanent magnet cannot be, is not going to be the same makeup as an AC transformer core, which is designed to lose its remanence immediately once the magnetism of the primary, let's say, is reduced to zero. We don't want that. We want a material that's suitable for a permanent, a perpetual motion holder. That's it. A perpetual motion holder experiment popularized by Edward Leeds Collin. Yet we want to take a step beyond that, because that's just a temporary situation. We want a permanent magnet. And then we use the additional iron that Edward Leeds Collin demonstrated in his perpetual motion holder experiment only as an additive magnetic capacitance, which we can get anyway by connecting capacitors to the transformer by shorting it out in pairs. You need two capacitors to short out each transformer with itself against the two terminals of, let's say, its primary on one side, and then another pair, let's see if I have that right. No, actually, it's only one capacitor. Oh, let me think. Right, no, oh, well, no, two capacitors, one shorting out the primary and one shorting out the secondary. So we treat it like a motor, in which we have a capacitor across the motor in parallel with the motor coil. Now, this is in addition to capacitors that are in series, a pair of capacitors that are in series connecting the terminals of the transformer to something else. Now, that something else could be the same model, creating a daisy chain of loops of Eric Dollard's analog computer in LMD mode, but it's more than LMD mode, because now it has capacitors shorting out each coil of the transformers, linking the daisy chain of analog computer and LMD modes together. And you need those capacitors shorting out the coils of each coil of each transformer in order to initiate over unity. Initiation is the hardest thing. Once you get that going, everything is clear sailing. It'll simply build up. But getting it started is the hardest part. And this is basically Bewley's archetype, a modified version of Eric Dollard's analog computer in LMD mode that has a ring of capacitors, of 4 capacitors, and on opposite capacitors, on the pair of capacitors opposed to each other, just one pair, we have positioned the transformers, linking each 4 capacitor loop together with the next 4 capacitor loop through magnetic coupling. But the capacitors are isolated, electrically isolated from each other, each ring of 4 capacitors. Only magnetic coupling joins them together. And the Bewley archetype is superb, but it's so powerful that it explodes. Unlike if the transformers are ideal. Now, I just stated that the use of the capacitors creates them in an ideal state. So I suspect that if we take out the extra pair of capacitors that are shorting out the coils of the transformer and replace it with a humongous amount of iron with lots of surface area undergoing remanence, that anything short of infinite mass of iron will not give us an explosive condition. And I think this is the distinct difference between the two opportunities that we can use to take advantage of to create magnetic capacitance in a analog computer situation of LMD orientation or modality. As an example, this idea of having 2 capacitors in series on either terminal of a coil, just a single coil to speak of, is a very powerful situation when the capacitance is low and the inductance is high. But that's only with a singular coil and 2 capacitors, one at each end, in series. If we have Eric's situation of an analog computer in LMD mode, it changes everything. And if we take it one step further to a Bewley archetype, now we got to put a braking mechanism on this thing to prevent it from exploding. And I found that to be resistors, diodes, and batteries, particularly batteries that we are attempting to recharge. They act as good braking mechanisms as well, even if they're relatively dead in the sense that they give out very weak charge, but not enough to power an appliance, but enough to at least be there in residual form. And I've done this study in Paul Falstad's simulator of a Bewley archetype applied to the situation of recharging batteries. But I'm using batteries as a type of resistor. But I have them, in addition to diodes, to make sure the orientation is to recharge the batteries and prevent them from discharging. And I think I might have even put resistors to help regulate the situation as well, and switches, flipping analog switches, flipping open and closed to prevent a runaway condition. So I can't remember. I'll have to look up what the switching speed was, because it might have been something ridiculous that's not mechanically possible. But there are workaround solutions. So, well, that's what transistors do, but then there's a problem. How do you prevent frying transistors if you're dealing with very high surges? No, there's another situation I have to bring up. And that is, how do you regenerate nickel metal hydride batteries? Because all of this is related to each other. I was trying to figure out how to revive the dead batteries in my RAV4 EV from 2002. Now that Battery MD up in Sacramento, run by Kit Rodden, no longer is in existence, in business, because there's not enough RAV4 EVs from that era, the first generation, to warrant his remaining in business. So now I'm stuck with a car in storage whose batteries cannot hold a charge more than 5 seconds or an instant. How do I regenerate them on my own? And I think the trick is to use extremely low voltage in the beginning, let's say 1/10 of environmental background voltage, which is somewhere around in the microvolt range. So 1/10 of a microvolt is, what is that? That's 100 nanovolts. Or it could be less, but something really small so as not to damage anything to start out with. And then use a frequency of pulses. They could be square wave pulses for all I care. But the frequency speed is significant. It has to be somewhere, to play it safe, somewhere up in the range of 10,000 cycles per second. And just start out with that. Let's see, what else? Well, yeah, in charging the batteries using an extremely low voltage and restrict the current so that with humongous resistance so that no current can get through. And I guess the only way to do that is with capacitors, because any high-level resistor is very hard to come by and very expensive and could probably get fried at some point anyway as it slowly wears down, and then its wear-down rate could probably accelerate, and then we'd have problems. So I think capacitors would be the only way to do this, to block the DC flow so that there'd be no current coming and going to the battery. And then we add diodes to make it one-way flow. If any residual current that might be there, that might be the best way to do it. But to get the switching speed, the oscillations, so up at around 10,000, and so any residual current will only go in one direction. The voltage, of course, will be massaging in opposite directions, and it'll be at a high rate and very weak voltage. And this is to try to get all of the crystallization, I suppose, shook up inside the battery, to get it loosened up so that its ossification status becomes more flexible, because that's what's preventing the batteries from becoming recharged. And that might be all that's needed over a certain length of time. And then that to regenerate the batteries and make them capable of holding a charge. And now when it comes to recharging them, they should be recharged correctly, which means high voltage, low current. They should never have high current applied and just a minimum amount of voltage. That's ages the battery and creates the problems in the first place of them losing the ability to store a charge. And it should probably be pulses. There are a lot of these pulsing available on the internet, on Amazon, that pulse charge a battery, but they don't do the configuration that I've explained at a high enough frequency and a low enough voltage and a blockage of current. That I don't think they do. In any case, whatever method is used for regeneration, basically, by way of extension, has to be the same method used for recharging them in order to preserve the life of the battery and not destroy it in the course of recharging it. So that terminates this recording.